As a car or truck moves over the road, the layer of silt is kicked up, creating a thick cloud of dust. Although the suspended load is usually deposited relatively near its source, high winds are capable of carrying large quantities of dust great distances. In the 1930s, silt that was picked up in Kansas was transported to New England and beyond, into the North Atlantic. Similarly, dust blown from the Sahara has been traced as far as the Caribbean. These are two dramatic examples of suspended load. Dust storms can cover huge areas, and dust can be transported great distances. Black and white image courtesy of USDA Natural Resources Conservation Service, satellite image. Courtesy of NASA. Erosional features. Smart Figure 16.10 Wind suspended load. Watch video, Wind suspended load. Compared to running water and glaciers, wind is a relatively modest force in sculpting landforms. Recall that even in deserts, most erosion is performed by intermittent running water, not by wind. Nevertheless, features created by wind erosion are significant elements of some landscapes. Deflation and blowouts. One way that wind erodes is by deflation, the lifting and removal of loose material. Deflation sometimes is difficult to notice because the entire surface is being lowered at the same time, but it can be significant. In portions of the 1930s Dust Bowl, vast areas of land were lowered by as much as 1 meter in only a few years. The most noticeable results of deflation in some places are shallow depressions appropriately called blowouts. In the Great Plains region, from Texas north to Montana, thousands of blowouts are visible on the landscape. They range from small dimples less than 1 meter deep and 3 meters wide to depressions that approach 50 meters deep and several kilometers across. The factor that controls the depths of these basins is the local water table. When blowouts are lowered to the water table, damp ground and vegetation prevent further deflation. Deflation is especially effective in creating these depressions when the land is dry and largely unprotected by anchoring vegetation. Figure 16.11 Blowouts. Did you know? The driest place on Earth is in Chile's Atacama Desert, a narrow belt of dry land that extends along the Pacific coast of South America. The town of Arica has an average rainfall of just 0.03 inches per year. Over a span of 59 years, this region received a total of less than 2 inches of rain. Desert pavement. In portions of many deserts, the surface consists of a closely packed layer of coarse particles. This veneer of pebbles and cobbles, called desert pavement, is only 1 or 2 stones thick. Beneath is a layer containing a significant proportion of silt and sand. When desert pavement is present, it is an important control on wind erosion because pavement stones are too large for deflation to remove. When this armor is disturbed, wind can easily erode the exposed fine silt. This closely packed veneer of pebbles and cobbles is only 1 or 2 stones thick. It is underlain by material containing a significant proportion of finer particles. For many years, the most common explanation for the formation of desert pavement was that it develops when wind removes sand and silt from poorly sorted surface deposits. As Figure 16.13a illustrates, the concentration of larger particles at the surface gradually increases as the finer particles are blown away. Eventually the surface is completely covered with pebbles and cobbles too large to be moved by the wind. Figure 16.12 Desert pavement. This model shows an area with poorly sorted surface deposits. Over time, deflation lowers the surface, and coarse particles become concentrated. In this model, the surface is initially covered with cobbles and pebbles. Over time, wind-blown dust accumulates at the surface and gradually sifts downward. Smart Figure 16.13 Full alternative text description. Smart Figure 16.13 Formation of desert pavement. Watch tutorial, Desert pavement. Studies have shown that the process depicted in Figure 16.13a is not an adequate explanation for all environments in which desert pavement exists. For example, in many places, desert pavement is underlain by a relatively thick layer of silt that contains few if any pebbles and cobbles. In such a setting, deflation of fine sediment could not leave behind a layer of coarse particles. Geologists have also found that in some areas, the pebbles and cobbles composing desert pavement have all been exposed at the surface for about the same length of time. This would not be the case for the process shown in Figure 16.13a. Here, the coarse particles that make up the pavement reach the surface over an extended time span, as deflation gradually removes the fine material. As a result, an alternate explanation for desert pavement was formulated. This hypothesis suggests that pavement develops on a surface that initially consists of coarse particles. Over time, protruding cobbles trap fine, wind-blown grains that settle and sift downward through the spaces between the larger surface stones. The process is aided by infiltrating rainwater. In this model, the cobbles composing the pavement were never buried. Moreover, it successfully explains the lack of coarse particles beneath the desert pavement. Ventifacts and yardangs. Like glaciers and streams, wind also erodes by abrasion. In dry regions as well as along some beaches, wind-blown sand cuts and polishes exposed rock surfaces. Abrasion sometimes creates interestingly shaped stones called ventifacts. The side of such a stone that is exposed to the prevailing wind is abraded, leaving it polished, pitted, and with sharp edges. If the wind is not consistently from one direction or if the pebble becomes reoriented, the stone may have several faceted surfaces. The sandblasting effect of the wind creates ventifacts and yardangs. Figure 16.14 Shaped by the wind. Unfortunately, abrasion often gets credit for accomplishments beyond its capabilities. Such features as balanced rocks that stand high atop narrow pedestals and intricate detailing on tall pinnacles are not the results of abrasion. Sand seldom travels more than 1 meter above the surface, so the wind's sandblasting effect is obviously limited in vertical extent. In addition to creating ventifacts, wind erosion is responsible for creating much larger features, called yardangs. A yardang is a streamlined, wind-sculpted landform that is oriented parallel to the prevailing wind. Individual yardangs are generally small features that stand less than 5 meters high and no more than about 10 meters long. Because the sandblasting effect of wind is greatest near the ground, these abraded bedrock remnants are usually narrower at their base. Sometimes yardangs are large features. Peru's Inca Valley contains yardangs that approach 100 meters in height and several kilometers in length. Some yardangs in the desert of Iran reach 150 meters in height. Concept check 16.4. 1. Describe the way in which wind transports sand. When winds are strong, how high above the surface can sand be carried? 2. How does wind suspended load differ from its bed load? 3. Why is wind erosion relatively more important in dry regions than in humid areas? 4. What factor limits the depths of blowouts? 5. Briefly describe 2 hypotheses used to explain the formation of desert pavement. 6. What are yardangs and ventifacts? 16.5 Wind deposits. Discuss the formation and movement of dunes and distinguish among different dune types. Explain how loess deposits differ from deposits of sand. Although wind is relatively unimportant in producing erosional landforms, significant depositional landforms are created by the wind in some regions. Accumulations of wind-blown sediment are particularly conspicuous in the world's dry lands and along many sandy coasts. Wind deposits are of 2 distinctive types: mounds and ridges of sand from the wind's bed load, which we call dunes, and extensive blankets of silt, called loess, that once were carried in suspension. Sand deposits. As is the case with running water, wind drops its load of sediment when velocity falls and the energy available for transport diminishes. Thus, sand begins to accumulate wherever an obstruction across the path of the wind slows its movement. Unlike many deposits of silt, which form blanket-like layers over large areas, winds commonly deposit sand in mounds or ridges called dunes. The dunes at this landmark in southeastern New Mexico are composed of gypsum. The dunes slowly migrate with the wind. Smart Figure 16.15 Full alternative text description. Smart Figure 16.15 White Sands National Monument. Moving air encountering an object, such as a clump of vegetation or a rock, sweeps around and over the object, leaving a shadow of slower moving air behind the obstacle and a smaller zone of quieter air just in front of the obstacle. Some of the saltating sand grains moving with the wind come to rest in these wind shadows. As the accumulation of sand continues, it becomes a more imposing barrier to the wind and thus a more efficient trap for even more sand. If there is a sufficient supply of sand and the wind blows steadily for a long enough time, the mound of sand grows into a dune. Many dunes have an asymmetrical profile, with the leeward slope being steep and the windward slope more gently inclined. The dunes in Figure 16.15 are a good example. Sand moves up the gentler slope on the windward side by saltation. Just beyond the crest of the dune, where the wind velocity is reduced, the sand accumulates. As more sand collects, the slope steepens, and eventually some of it slides under the pull of gravity. In this way, the leeward slope of the dune, called the slip face, maintains an angle of about 34 degrees, the angle of repose for loose dry sand. Continued sand accumulation, coupled with periodic slides down the slip face, results in the slow migration of the dune in the direction of air movement. Watch Mobile Field Trip, The Dunes of White Sands National Monument. Did you know? Deserts don't necessarily consist of mile after mile of drifting sand dunes. Surprisingly, sand accumulations represent only a small percentage of the total desert area. For example, dunes cover only 1/10 of the Sahara's area. The sandiest of all deserts, the Arabian, is 1/3 sand-covered. As sand is deposited on the slip face, layers form that are inclined in the direction the wind is blowing. These sloping layers are called crossbeds. When the dunes are eventually buried under other layers of sediment and become part of the sedimentary rock record, their asymmetrical shape is destroyed, but the crossbeds remain as testimony to their origin. Nowhere is crossbedding more prominent than in the sandstone walls of Zion Canyon in southern Utah. As sand is deposited on the slip face, layers form that are inclined in the direction the wind is blowing. With time, complex patterns develop in response to changes in wind direction. Smart Figure 16.16 Crossbedding. Smart Figure 16.16 Full alternative text description. Watch tutorial, Dune movement. Types of sand dunes. Dunes are not just random heaps of wind-blown sediment. Rather, they are accumulations that usually assume patterns that are surprisingly consistent. Addressing this point, a leading early investigator of dunes, the British engineer R. Bagnall, observed, instead of finding chaos and disorder, the observer never fails to be amazed at a simplicity of form, an exactitude of repetition, and a geometric order. Dunes come in a wide assortment of forms, and some irregular dunes do not fit easily into any category. For simplicity, we will consider just the 6 basic dune types shown in Figure 16.17. Several factors influence the form and size that dunes ultimately assume. These include wind direction and velocity, availability of sand, and the amount of vegetation present. Factors that influence the form and size of dunes include wind direction and velocity, the availability of sand, and the amount of vegetation. Smart Figure 16.17 Types of sand dunes. Smart Figure 16.17 Full alternative text description. Barcon dunes. Watch tutorial, dune types. Solitary sand dunes shaped like crescents and with their tips pointing downwind are called Barcon dunes. These dunes form where supplies of sand are limited and the surface is relatively flat, hard, and lacking vegetation. They migrate slowly with the wind at a rate of up to 15 meters per year. Their size is usually modest, with the largest barcons reaching heights of about 30 meters, while the maximum spread between their tips approaches 300 meters. When the wind direction is nearly constant, the crescent form of these dunes is nearly symmetrical. However, when the wind direction is not perfectly fixed, one tip becomes larger than the other. Transverse dunes. In regions where the prevailing winds are steady, sand is plentiful, and vegetation is sparse or absent, the dunes form a series of long ridges that are separated by troughs and oriented at right angles to the prevailing wind. Because of this orientation, they are termed transverse dunes. Many coastal dunes are of this type. In addition, transverse dunes are common in many arid regions where the extensive surface of wavy sand is sometimes called a sand sea. In some parts of the Sahara and Arabian deserts, transverse dunes reach heights of 200 meters, are 1 to 3 kilometers across, and can extend for distances of 100 kilometers or more. There is a relatively common dune form that is intermediate between isolated barcons and extensive waves of transverse dunes. Such dunes, called barconoid dunes, form scalloped rows of sand oriented at right angles to the wind. The rows resemble a series of barcons that have been positioned side by side. Longitudinal dunes. Long ridges of sand that form more or less parallel to the prevailing wind where sand supplies are moderate are called longitudinal dunes. Apparently, the prevailing wind direction must vary somewhat but still remain in the same quadrant of the compass. Although the smaller types are only 3 or 4 meters high and several dozens of meters long, in some large deserts, longitudinal dunes can reach great size. For example, in portions of North Africa, Arabia, and Central Australia, these dunes may approach a height of 100 meters and extend for distances of more than 100 kilometers. Parabolic dunes. Unlike the other dune types described thus far, parabolic dunes form where vegetation partially covers the sand. The shape of these dunes resembles the shape of barcons except that their tips point into the wind rather than downwind. Parabolic dunes often form along coasts where there are strong onshore winds and abundant sand. If the sand's sparse vegetative cover is disturbed at some spot, deflation creates a blowout. Sand is then transported out of the depression and deposited as a curved rim, which grows higher as deflation enlarges the blowout. Star dunes. Confined largely to parts of the Sahara and Arabian deserts, star dunes are isolated hills of sand that exhibit a complex form. Their name is derived from the fact that the bases of these dunes resemble multipoint stars. Usually 3 or 4 sharp-crested ridges diverge from a central high point that in some cases may approach a height of 90 meters. As their form suggests, star dunes develop where wind directions are variable. Loess deposits. In some parts of the world, the surface topography is mantled with deposits of windblown silt called loess. Over periods of perhaps thousands of years, dust storms deposited this material. When loess is breached by streams or road cuts, it tends to maintain vertical cliffs and lacks any visible layers, as you can see in Figure 16.18. In some regions, the surface is mantled with deposits of windblown silt. The distribution of loess worldwide indicates that there are 2 primary sources for this sediment: deserts and glacial outwash deposits. The thickest and most extensive deposits of loess on Earth occur in western and northern China. They were blown there from the extensive desert basins of Central Asia. Accumulations of 30 meters are common and thicknesses of more than 100 meters have been measured. It is this fine, buff-colored sediment that gives the Yellow River its name. Figure 16.18 Loess. In the United States, deposits of loess are significant in many areas, including South Dakota, Nebraska, Iowa, Missouri, and Illinois, as well as portions of the Columbia Plateau in the Pacific Northwest. The correlation between the distribution of loess and important farming regions in the Midwest and eastern Washington state is not just a coincidence because soils derived from this wind-deposited sediment are among the most fertile in the world. Did you know? The highest dunes in the world are located along the southwest coast of Africa, in the Namib Desert. In places, these huge dunes reach heights of 1,000 to 1,167 feet. The dunes at Great Sand Dunes National Park in southern Colorado are the highest in North America, rising more than 700 feet above the surrounding terrain. Unlike the deposits in China, which originated in deserts, the loess in the United States and Europe is an indirect product of glaciation. Its source is deposits of stratified drift. During the retreat of the ice sheets, many river valleys were choked with sediment deposited by meltwater. Strong westerly winds sweeping across the barren floodplains picked up the finer sediment and dropped it as a blanket on the eastern sides of the valleys. Such an origin is confirmed by the fact that loess deposits are thickest and coarsest on the leeward side of such major glacial drainage outlets as the Mississippi and Illinois rivers and rapidly thin with increasing distance from the valleys. Furthermore, the angular, mechanically weathered particles composing the loess are essentially the same as the rock flour produced by the grinding action of glaciers. Concept check 16.5. 1. How do sand dunes migrate? 2. List and briefly distinguish among basic dune types. 3. How is loess different from sand? 4. How are some loess deposits related to glaciers? Concepts in review, deserts and wind. 16.1 Distribution and causes of dry lands. Describe the general distribution of Earth's dry lands and explain why deserts form in the subtropics and middle latitudes. Key terms. Dry climate desert steppe rain shadow. Dry climates cover about 30% of Earth's land area. These regions have yearly precipitation totals that are less than the potential loss of water through evaporation. Evaporation depends on temperature, and deserts may occur in hot or cold climates. Deserts are drier than steppes, but both climatic types are considered water deficient. Dry climates in subtropical latitudes are associated with the global distribution of air pressure and winds. Near the equator, warm, moist air rises and then moves to 20 or 30 latitude before sinking back toward Earth's surface. The subsiding air brings clear skies, copious sunshine, and dry conditions to these zones of subtropical high pressure. Deserts also occur in continental interiors of the middle latitudes. Most are subject to the rainshadow effect, in which moist air moving inland from oceans is intercepted by mountainous obstacles. As the air is forced to rise, it cools, producing clouds and precipitation on the windward slopes. By contrast, the leeward side, called the rainshadow, tends to be quite dry. This map shows annual precipitation across the continent of Africa. At which latitudes is the atmosphere rising? At which latitudes is it sinking? How does this atmospheric circulation influence the continent's climates? Figure 16.7-1 Full alternative text description. 16.2 Geologic processes in arid climates. Summarize the geologic roles of weathering, running water, and wind in arid and semi-arid climates. Key term. Ephemeral stream. In dry lands, rock weathering of any type is greatly reduced because of the lack of water and the scarcity of organic acids from decaying plants. Practically all desert streams are dry most of the time and are said to be ephemeral. Their channels are carved out largely by flash floods that occur during sporadic storm events. Permanent desert streams originate in wetter climates. They must carry a great volume of water to keep from losing all their water as they cross the desert. Running water is responsible for most of the erosional work in a desert. Although wind erosion is more significant in dry areas than in other environments, it still cannot match running water as an agent of erosion in deserts. This is a typical desert stream shortly after a heavy rain. What term is applied to such a stream? How will this scene likely change in the near future? 16.3 Basin and Range, the evolution of a desert landscape. Discuss the stages of landscape evolution in the basin and range region of the western United States. Key terms. Interior drainage alluvial fan Bajada Playa Lake Playa Inselberg. The basin and range region is a distinctive area of western North America that demonstrates some key principles of mountainous desert landscapes. The mountain ranges and intervening valleys were produced through normal faulting, but then the rock mass of the mountain ranges was redistributed by weathering, erosion, transportation, and deposition. With sufficient time, the overall effect is to reduce topographic relief by grinding down the mountains and depositing the sedimentary debris in the low-lying basins. Alluvial fans form during the early stage of arid landscape development, when the relief is highest. Over time, these fans grow and merge, so that by the middle stage, continuous bajadas of sediment cover the line where the ranges meet the basins. On the basin floor, playa lakes may form during wet periods and then dry up to produce salty playas. When almost all of the mountains have been worn down and most of the low-lying basins have been filled in with sediment, the landscape has reached the late stage of development. It is then marked by isolated inselbergs of bedrock poking up through a sea of sediment. Identify the lettered features in this photo. How did they form? 16.4 Wind erosion. Describe the ways that wind transports sediment and the processes and features associated with wind erosion. Key terms. Bed load saltation suspended load deflation blowout desert pavement abrasion ventifact yardang. A current of air can pick up and transport sediment, though with a lower competence than a current of water or glacial ice. Wind cannot pick up the coarser particles that water can, but it is capable of transporting sediment over vast areas and even high into the atmosphere. A portion of the sediment transported by wind is bed load that bounces along Earth's surface. Generally, these saltating particles of sand never get more than 0.5 meter above the ground. Other sediment is fine-grained enough to stay suspended in the air. Clay and silt are both small enough particles that they can be carried as suspended load. Once aloft, they can be carried tremendous distances, across entire continents and ocean basins. Wind is capable of erosion, though it should be emphasized that water is the most important agent of erosion in desert regions. The Dust Bowl is a classic example of a massive episode of soil erosion by wind during the 1930s. Localized deflation may produce shallow depressions known as blowouts. Desert pavement is a thin layer of coarse pebbles and cobbles that covers some desert surfaces. Two models have been proposed to explain the formation of desert pavement: a model in which deflation strips the finer grains from a deposit of poorly sorted sediments, and an additive model in which pebbles and cobbles trap smaller wind-blown grains in the spaces between them. Ventifacts are produced when individual rocks become abraded by wind-blown sediment, giving the rocks a polished, pitted surface. This effect is most pronounced on the side that faces the prevailing wind. Similar sandblasting of the land surface may sculpt rock outcrops into streamlined yardangs that are longest parallel to the prevailing wind direction. This satellite image shows a large plume of wind-blown sediment over portions of Iran, Afghanistan, and Pakistan in March 2012. Is the wind-transported material in the image more likely bed load or suspended load? What term is applied to the erosional process that was responsible for producing this plume? 16.5 Wind deposits. Discuss the formation and movement of dunes and distinguish among different dune types. Explain how loess deposits differ from deposits of sand. Key terms. Dune slip face crossbed barcon dune transverse dune barconoid dune longitudinal dune parabolic dune star dune loess. Wind deposits are of two distinct types, mounds and ridges of sand, called dunes, which are formed from sediment that is carried as part of the wind's bed load, and extensive blankets of silt, called loess, carried by wind in suspension. Dunes accumulate due to the differences in wind energy on the upwind and downwind sides of some obstacle. Wind moves sand up the more gently sloping upwind side, across the crest of the dune, where it settles out in the calmer air on the downwind side of the dune, the steeply sloped slip face. When the sand on the slip face piles up past the angle of repose, it spontaneously collapses in small avalanches of sand. Over time, this causes a dune to slowly move in the direction of the prevailing wind, with the slip face leading the way. Inside the dune, the buried slip faces may be preserved as crossbeds. Loess is windblown silt, deposited over large areas sometimes in thick blankets. Most loess is derived from either deserts or areas that have recently been glaciated. Winds blow across stratified drift and pick up silt-sized grains, carrying them in suspension to the site of deposition. There are 6 major kinds of dunes. Their shapes result from the pattern of prevailing winds, the amount of available sand, and the presence of vegetation. This is an aerial view of a dune in northern Arizona. Which one of the basic dune types is it? Sketch a simple profile of this dune. Include an arrow to show the prevailing wind direction and label the dune's slip face. Give it some thought. 1. Albuquerque, New Mexico, receives an average of 20.7 centimeters of rainfall annually. Albuquerque is considered a desert under the commonly used Köppen climate classification. The Russian city of Verkhoyansk is located near the Arctic Circle in Siberia. Yearly precipitation at Verkhoyansk averages 15.5 centimeters, about 5 centimeters less than Albuquerque, yet it is classified as a humid climate. Explain why this is the case. 2. Compare and contrast the sediment deposited by a stream, wind, and a glacier. Which deposit should have the most uniform grain size? Which one would exhibit the poorest sorting? Explain your choices. 3. Is either of the following statements true? Are they both true? Explain your answer. Wind is more effective as an agent of erosion in dry places than in humid places. B. Wind is the most important agent of erosion in deserts. 4. Examine the precipitation map for the state of Nevada. Notice that the areas receiving the most precipitation resemble long, slender islands scattered across the state. Provide an explanation for this pattern. Figure 16.7-1 Full alternative text description. 5. This satellite image shows a small portion of the Zagros Mountains in dry southern Iran. Streams in this region flow only occasionally. The green tones on the image identify productive agricultural areas. A. Identify the large feature that is labeled with a question mark. B. Explain how the feature named in question is formed. C. What term is used to describe streams like the ones that occur in this region? D. Speculate on the likely source of water for the agricultural areas in this image. 6. Bryce Canyon National Park, shown in this photo, is in dry southern Utah. It is carved into the eastern edge of the Paunsaugen Plateau. Erosion has sculpted the colorful limestone into bizarre shapes, including spires called hoodoos. As you and a non-geologist companion are viewing the scenery in Bryce Canyon, your friend says, "It's amazing how wind has created this incredible scenery." Now that you have studied arid landscapes, how would you respond to your companion's statement? Mastering Geology trademark. Looking for additional review and test prep materials? Visit the study area in Mastering Geology to enhance your understanding of this chapter's content by accessing a variety of resources, including self-study quizzes, geoscience animations, smart figures, mobile field trips, Project Condor quadcopter videos, in the news RSS feeds, flashcards, web links, and an optional Pearson e-text. Chapter 17 Shorelines. In contrast to the gently sloping coastal plains of the Atlantic and Gulf coasts, the Pacific coast is characterized by relatively narrow beaches that are often backed by steep cliffs and mountain ranges. These crashing waves and sea stacks are at Soberane's Point along the California coast. Focus on concepts. Each statement represents the primary learning objective for the corresponding major heading within the chapter. After you complete the chapter, you should be able to 17.1 Explain why the shoreline is considered a dynamic interface. List the factors that influence the height, length, and period of a wave and describe the motion of water within a wave. 17.2 Explain how waves erode and move sediment along the shore. 17.3 Describe the features typically created by wave erosion and those resulting from sediment deposited by longshore transport processes. 17.4 Distinguish between emergent and submergent coasts. Contrast the erosion problems faced on the Atlantic and Gulf coasts with those along the Pacific coast. 17.5 Describe the basic structure and characteristics of a hurricane and the three broad categories of hurricane destruction. 17.6 Summarize the ways in which people deal with shoreline erosion problems. 17.7 Explain the cause of tides and their monthly cycles. Describe the horizontal flow of water that accompanies the rise and fall of tides. The restless waters of the ocean are constantly in motion. Winds generate surface currents, the gravity of the moon and sun produces tides, and density differences create deep ocean circulation. Further, waves carry the energy from storms to distant shores, where their impact erodes the land. Shorelines are dynamic environments. Their topography, geologic makeup, and climate vary greatly from place to place. Continental and oceanic processes converge along the shore to create landscapes that frequently undergo rapid change. When it comes to the deposition of sediment, shore areas are transition zones between marine and continental environments. 17.1 The shoreline and ocean waves. Explain why the shoreline is considered a dynamic interface. List the factors that influence the height, length, and period of a wave and describe the motion of water within a wave. The shoreline is the line that marks the contact between land and sea. Each day, as tides rise and fall, the position of the shoreline migrates. Over longer time spans, as sea level rises or falls, the average position of the shoreline gradually shifts. A dynamic interface. Nowhere is the restless nature of the ocean more noticeable than along the shore, the dynamic interface among air, land, and sea. An interface is a common boundary where different parts of a system interact. This is certainly an appropriate designation for the coastal zone. Here we can see the rhythmic rise and fall of tides and observe waves constantly rolling in and breaking. Sometimes the waves are low and gentle. At other times they pound the shore with awesome fury. Although it may not be obvious, the shoreline is constantly being modified by waves. Crashing surf erodes the land. Wave activity also moves sediment toward and away from the shore, as well as along it. Such activity sometimes produces narrow sandbars and fragile offshore islands that frequently change size and shape as storm waves come and go. The nature of present-day shorelines is not just the result of the relentless attack of the land by the sea. Rather, the shore has a complex character that results from multiple geologic processes. For example, practically all coastal areas were affected by the worldwide rise in sea level that accompanied the melting of ice sheets following the last glacial maximum. As the sea encroached landward, the shoreline retreated, becoming superimposed upon existing landscapes that had resulted from such diverse processes as stream erosion, glaciation, volcanic activity, and the forces of mountain building. Today the coastal zone is experiencing intensive human activity. Unfortunately, people often treat the shoreline as if it were a stable platform on which structures can safely be built. This attitude inevitably leads to conflicts between people and nature. As you will see, many coastal landforms, especially beaches and barrier islands, are relatively fragile, short-lived features that are inappropriate sites for development. The image of the New Jersey shoreline in Figure 17.2 is an example. Bluff failure caused by storm waves in March 2016 resulted in these apartments in Pacifica, California, being condemned. When these buildings were erected in the 1970s, they were safely away from the cliffs. Over the years, several measures were attempted to reduce erosion of the sandstone cliffs. All proved to be inadequate. Figure 17.1 Teetering on the edge. A portion of the New Jersey shoreline shortly after this huge storm struck in late October 2012. The extraordinary storm surge caused much of the damage pictured here. Many shoreline areas are intensively developed. Often the shifting shoreline sands and the desire of people to occupy these areas are in conflict. Ocean waves. Figure 17.2 Hurricane Sandy. Ocean waves travel along the interface between ocean and atmosphere. They can carry energy from a storm far out at sea over distances of several thousand kilometers. That's why even on calm days, the ocean still has waves that travel across its surface. When observing waves, always remember that you are watching energy travel through a medium. If you make waves by tossing a pebble into a pond, or by splashing in a pool, or by blowing across the surface of a cup of coffee, you are imparting energy to the liquid, and the waves you see are the visible evidence of the energy passing through. Wind-generated waves provide most of the energy that shapes and modifies shorelines. Where the land and sea meet, waves that may have traveled unimpeded for hundreds or thousands of kilometers suddenly encounter a barrier that will not allow them to advance farther and must absorb their energy. Stated another way, the shore is the location where a practically irresistible force confronts an almost immovable object. The conflict that results is never-ending and sometimes dramatic. Wave characteristics. Most ocean waves derive their energy and motion from the wind. When a breeze is less than 3 km per hour, only small wavelets appear. At greater wind speeds, more stable waves gradually form and advance with the wind. Characteristics of ocean waves are illustrated in Figure 17.3, which shows a simple, non-breaking wave form. The tops of the waves are the crests, which are separated by troughs. Halfway between the crests and troughs is the still water level, which is the level the water would occupy if there were no waves. The vertical distance between trough and crest is called the wave height, and the horizontal distance between successive crests is the wavelength. The time it takes one full wave, one wavelength, to pass a fixed position is the wave period. An idealized non-breaking wave, showing its basic parts and the movement of water with increasing depth. Smart Figure 17.3 Full alternative text description. Smart Figure 17.3 Wave basics. Watch animation, wave basics. The height, length, and period that are eventually achieved by a wave depend on three factors: the wind speed, the length of time the wind has blown, and the fetch, or the distance the wind has traveled across open water. As the quantity of energy transferred from the wind to the water increases, the height and steepness of the waves increase as well. Eventually a critical point is reached where waves grow so tall that they topple over, forming ocean breakers called whitecaps. Did you know? About half of the world's human population lives on or within 60 miles of a coast. The proportion of the U.S. population residing within 45 miles of a coast is well in excess of 50%. The concentration of such large numbers of people so near the shore means that hurricanes and tsunamis place millions at risk. For a particular wind speed, there is a maximum fetch and duration of wind beyond which waves will no longer increase in size. When the maximum fetch and duration are reached for a given wind velocity, the waves are said to be fully developed. The reason that waves can grow no further is that they are losing as much energy through the breaking of whitecaps as they are receiving from the wind. When wind stops or changes direction, or when waves leave the stormy area where they were created, the waves continue on without relation to local winds. The waves also undergo a gradual change to swells, which are lower and longer and may carry a storm's energy to distant shores. Because many independent wave systems exist at the same time, the sea surface acquires a complex, irregular pattern. Hence, the sea waves we watch from the shore are often a mixture of swells from faraway storms and waves created by local winds. Circular orbital motion. Waves can travel great distances across ocean basins. In one study, waves generated near Antarctica were tracked as they traveled through the Pacific Ocean basin. After more than 10,000 kilometers, the waves finally expended their energy a week later, along the shoreline of the Aleutian Islands of Alaska. The water itself doesn't travel this distance, but the waveform does. As the wave travels, the water passes the energy along by moving in a circle. This movement is called circular orbital motion. Observation of an object floating in waves reveals that it moves not only up and down but also slightly forward and backward with each successive wave. When the movement of the toy boat shown in Figure 17 is traced as a wave passes, it can be seen that the boat moves in a circle and returns to essentially the same place. Circular orbital motion allows a waveform to move forward through the water, while the individual water particles that transmit the wave move in a circle. Wind moving across a field of wheat causes a similar phenomenon. The wheat itself doesn't travel across the field, but the waves do. The movements of the toy boat show that the waveform advances, but the water does not advance appreciably from the original position. In this sequence, the wave moves from left to right as the boat rotates in an approximate circle. Smart Figure 17.4 Passage of a wave. The energy contributed by the wind to the water is transmitted not only along the surface of the sea but also downward. However, beneath the surface, the circular motion rapidly diminishes until, at a depth equal to 1/2 the wavelength measured from the still water level, the movement of water particles becomes negligible. This depth is known as the wave base. The dramatic decrease of wave energy with depth is shown by the rapidly diminishing diameters of water particle orbits in Figure 17.3. Watch tutorial, Wave Motion. Waves in the surf zone. As long as a wave is in deep water, it is unaffected by water depth. However, when a wave approaches the shore, the water becomes shallower and influences wave behavior. The wave begins to feel bottom at a water depth equal to its wave base. Such depths interfere with water movement at the base of the wave and slow its advance. Waves touch bottom as they encounter water depths that are less than half a wavelength. As a result, the wave speed decreases, and the faster-moving waves farther from shore begin to catch up, which causes the distance between waves to decrease. This causes an increase in wave height, to the point where the waves finally pitch forward and break in the surf zone. Smart Figure 17.5 Waves approaching the shore. Smart Figure 17.5 Full alternative text description. As a wave advances toward the shore, the slightly faster waves farther out to sea catch up, decreasing the wavelength. As the speed and length of the wave diminish, the wave steadily grows higher. Finally, a critical point is reached when the wave is too steep to support itself and the wavefront collapses, or breaks, causing water to advance up the shore. The turbulent water created by breaking waves is called surf. On the landward margin of the surf zone, the swash, the turbulent sheet of water from collapsing breakers, moves up the slope of the beach. When the energy of the swash has been expended, the water flows back down the beach toward the surf zone as backwash. Watch animation, wave motion and wave refraction. Concept check 17.1. 1. Why is the shoreline described as being an interface? 2. Aside from ocean waves, what other factors influence the nature of present-day shorelines? 3. List 3 factors that determine the height, length, and period of a wave. 4. Describe the motion of a floating object as a wave passes. 5. How do a wave's speed, wavelength, and height change as the wave moves into shallow water and breaks. 17.2 Beaches and shoreline processes. Explain how waves erode and move sediment along the shore. For many, a beach is the sandy area where people lie in the sun and walk along the water's edge. Technically, a beach is an accumulation of sediment found along the landward margin of a water body. Along straight coasts, beaches may extend for tens or hundreds of kilometers. Where coasts are irregular, beach formation may be confined to the relatively quiet waters of bays. Beaches are composed of whatever material is locally abundant. The sediment for some beaches is derived from the erosion of adjacent cliffs or nearby coastal mountains. Other beaches are built from sediment delivered to the coast by rivers. Although the mineral makeup of many beaches is dominated by durable quartz grains, other minerals may be dominant. For example, in areas such as southern Florida, where there are no mountains or other sources of rock-forming minerals nearby, most beaches are composed of shell fragments and the remains of organisms that live in coastal waters. Some beaches on volcanic islands in the open ocean are composed of weathered grains of basaltic lava or of coarse debris eroded from coral reefs that develop around islands in low latitudes. A beach is an accumulation of sediment on the landward margin of an ocean or a lake and can be thought of as material in transit along the shore. Beaches are composed of whatever material is locally available. Figure 17.6 Beaches. Regardless of the composition, the material that comprises a beach does not stay in one place. Instead, crashing waves are constantly moving it. Thus, beaches can be thought of as material in transit along the shore. Wave erosion. During calm weather, wave action is minimal. However, just as streams do most of their work during floods, so too do waves accomplish most of their work during storms. The impact of storm-induced waves against the shore can be awesome in its violence. Each breaking wave may hurl thousands of tons of water against the land, sometimes causing the ground to literally tremble. It is no wonder that cracks and crevices are quickly opened in cliffs, seawalls, breakwaters, and anything else that is subjected to these enormous shocks. Water is forced into every opening, causing air in the cracks to become highly compressed by the thrust of crashing waves. When the wave subsides, the air expands rapidly, dislodging rock fragments and enlarging and extending fractures. When large waves break against the shore, the force of the water can be powerful and the erosional work that is accomplished can be great. These storm waves are breaking along the coast of Wales. Figure 17.7 Storm waves. In addition to the erosion caused by wave impact and pressure, abrasion, the sawing and grinding action of the water armed with rock fragments, is also important. In fact, abrasion is probably more intense in the surf zone than in any other environment. Smooth, rounded stones and pebbles along the shore are obvious reminders of the relentless grinding action of rock against rock in the surf zone. The chapter opening photo and figure 17.8a are good examples. Further, the waves use such fragments as tools as they cut horizontally into the land. Breaking waves armed with rock debris can do a great deal of erosional work. Figure 17.8 Abrasion, sawing and grinding. Sand movement on the beach. Beaches are sometimes called rivers of sand. The energy from breaking waves often causes large quantities of sand to move roughly parallel to the shoreline, both along the beach face and in the surf zone. Wave energy also causes sand to move perpendicular to the shoreline. Movement perpendicular to the shoreline. If you stand ankle-deep in water at the beach, you will see that swash and backwash move sand toward and away from the shoreline. Whether there is a net loss or addition of sand depends on the level of wave activity. When wave activity is relatively light, much of the swash soaks into the beach, which reduces the backwash. Consequently, the swash dominates and causes a net movement of sand up the beach face. When high-energy waves prevail, the beach is saturated from previous waves, so much less of the swash soaks in. As a result, erosion occurs because backwash is strong and causes a net movement of sand down the beach face. Along many beaches, light wave activity is the rule during the summer. Therefore, a wide sandy beach gradually develops. During winter, when storms are frequent and more powerful, strong wave activity erodes and narrows the beach. A wide beach that may have taken months to build can be dramatically narrowed in just a few hours by the high-energy waves created by a strong winter storm. Wave refraction. The bending of waves, called wave refraction, plays an important part in shoreline processes. It affects the distribution of energy along the shore and thus strongly influences where and to what degree erosion, sediment transport, and deposition will take place. As waves first touch bottom in the shallows along an irregular coast, they are slowed, they then bend and align nearly parallel to the shoreline. Smart Figure 17.9 Wave Refraction. Smart Figure 17.9 Full alternative text description. The shore is seldom oriented exactly parallel to approaching ocean waves. Rather, most waves move toward the shore at an angle. However, when they reach the shallow water of a smoothly sloping bottom, they bend and tend to become parallel to the shore. Such bending occurs because the part of the wave nearest the shore reaches shallow water and slows first, whereas the end that is still in deep water continues forward at its full speed. The net result is a wave front that may approach nearly parallel to the shore, regardless of the original direction of the wave. Watch tutorial, Wave Refraction. Did you know? During a storm that struck the coast of Scotland, a 1,350-ton portion of a steel and concrete breakwater was torn from the rest of the structure and moved toward shore. 5 years later, the 2,600-ton unit that replaced the first met a similar fate. Because of refraction, wave impact is concentrated against the sides and ends of headlands that project into the water, whereas wave attack is weakened in bays. This differential wave attack along irregular coastlines is illustrated in Figure 17. 9. The shallow water near a headland causes waves to refract toward the headland, focusing their energy and also causing the waves to attack the headland from all three sides. By contrast, refraction in the bays causes waves to diverge and expend less energy. In these zones of weakened wave activity, sediments can accumulate and form sandy beaches. Over a long period, erosion of the headlands and deposition in the bays will straighten an irregular shoreline. Longshore transport. Although waves are refracted, most still reach the shore at some angle, however slight. Consequently, the uprush of water from each breaking wave is at an oblique angle to the shoreline. However, the backwash is straight down the slope of the beach. The effect of this pattern of water movement is to transport sediment in a zigzag pattern along the beach face. This movement is called beach drift, and it can transport sand and pebbles hundreds or even thousands of meters each day. However, a more typical rate is 5 to 10 meters per day. The two components of the transport system, beach drift and longshore currents, are created by breaking waves that approach the beach at an angle. These processes transport large quantities of material along the beach and in the surf zone. Smart Figure 17.10 The Longshore Transport System. Smart Figure 17.10 Full alternative text description. Waves that approach the shore at an angle also produce currents within the surf zone that flow parallel to the shore and move substantially more sediment than beach drift. Because the water here is turbulent, these longshore currents easily move the fine suspended sand and roll larger sand and gravel along the bottom. When the sediment transported by longshore currents is added to the quantity moved by beach drift, the total amount can be very large. At Sandy Hook, New Jersey, for example, the quantity of sand transported along the shore over a 48-year period averaged almost 750,000 tons annually. For a 10-year period in Oxnard, California, more than 1.5 million tons of sediment moved along the shore each year. Both rivers and coastal zones move water and sediment from one area to another. As a result, the beach has often been characterized as a river of sand. Beach drift and longshore currents, however, move in a zigzag pattern, whereas rivers flow mostly in a turbulent, swirling fashion. In addition, the direction of flow of longshore currents along a shoreline can change if the direction from which waves approach the beach changes, whereas rivers always flow in the same direction. Nevertheless, longshore currents generally flow southward along both the Atlantic and Pacific shores of the United States. Watch tutorial, Longshore Currents. Rip currents. Rip currents are concentrated movements of water that flow opposite the direction of breaking waves. Most of the backwash from spent waves finds its way back to the open ocean as an unconfined flow across the ocean bottom called sheet flow. However, sometimes a portion of the returning water moves seaward in the form of surface rip currents. These currents do not travel far beyond the surf zone before breaking up and can be recognized by the way they interfere with incoming waves or by the sediment that is often suspended within the rip current. They can be hazardous to swimmers, who, if caught in them, can be carried out away from shore. The best strategy for exiting a rip current is to swim parallel to the shore for a few tens of meters. These concentrated movements of water flow opposite the direction of breaking waves. Figure 17.11 Rip current. Concept check 17.2. 1. Why do waves approaching the shoreline often bend? 2. What is the effect of wave refraction along an irregular coastline? 3. Describe the two processes that contribute to longshore transport. 17.3 Shoreline features. Describe the features typically created by wave erosion and those resulting from sediment deposited by longshore transport processes. A fascinating assortment of shoreline features can be observed along the world's coastal regions. Although the same processes cause change along every coast, not all coasts respond in the same way. Interactions among different processes and the relative importance of each process depend on local factors, including the proximity of a coast to sediment-laden rivers, the degree of tectonic activity, the topography and composition of the land, prevailing winds and weather patterns, and the configuration of the coastline and nearshore areas. Features that originate primarily because of erosion are called erosional features, whereas accumulations of sediment produce depositional features. Erosional features. Many coastal landforms owe their origin to erosional processes. Such erosional features are common along the rugged and irregular New England coast and along the steep shorelines of the west coast of the United States. Wave-cut cliffs, wave-cut platforms, and marine terraces. As the name implies, wave-cut cliffs originate in the cutting action of the surf against the base of coastal land. As erosion progresses, rocks overhanging the notch at the base of the cliff crumble into the surf, and the cliff retreats. A relatively flat, bench-like surface, called a wave-cut platform, is left behind by the receding cliff. The platform broadens as wave attack continues. Some debris produced by the breaking waves remains along the water's edge as sediment on the beach, and the remainder is transported farther seaward. If a wave-cut platform is uplifted above sea level by tectonic forces, it becomes a marine terrace. Marine terraces are easily recognized by their gentle seaward sloping shape and are often desirable sites for coastal roads, buildings, or agriculture. Figure 17.12 Wave-cut platform and marine terrace. This wave-cut platform is exposed at low tide along the California coast at Bolinas Point near San Francisco. A wave-cut platform was uplifted to create the marine terrace. Sea arches and sea stacks. Because of refraction, waves vigorously attack headlands that extend into the sea. The surf erodes the rock selectively, wearing away the softer or more highly fractured rock at the fastest rate. At first, sea caves may form. When two caves on opposite sides of a headland unite, a sea arch results. Eventually the arch falls in, leaving an isolated remnant or sea stack on the wave-cut platform. In time, it too will be consumed by the action of the waves. These features at the tip of Mexico's Baja Peninsula resulted from vigorous wave attack on a headland. Depositional features. Sediment that is transported along the shore tends to be deposited in areas where wave energy is low. Such processes produce a variety of depositional features. Figure 17.13 Sea stack and sea arch. Spits, bars, and tombolos. Where beach drift and longshore currents are active, several features related to the movement of sediment along the shore may develop. A spit is an elongated ridge of sand that projects from the land into the mouth of an adjacent bay. Often the end of a spit that is in the water hooks landward in response to the dominant direction of the longshore current. The term behemoth bar is applied to a sandbar that completely crosses a bay, sealing it off from the open ocean. Such a feature tends to form across a bay where currents are weak, allowing a spit to extend to the other side. A tombolo, a ridge of sand that connects an island to the mainland or to another island, forms in much the same manner as a spit. A high-altitude image of a well-developed spit and behemoth bar along the coast of Martha's Vineyard, Massachusetts. B. This photograph, taken from the International Space Station, shows Provincetown Spit at the tip of Cape Cod. Smart figure 17.14 Coastal Massachusetts. Barrier Islands. The Atlantic and Gulf coastal plains are relatively flat and slope gently seaward. The shore zone is characterized by barrier islands. These low ridges of land parallel the coast at distances from 3 to 30 kilometers offshore. From Cape Cod, Massachusetts, to Padre Island, Texas, nearly 300 barrier islands rim the coast. Watch Mobile Field Trip, a trip to Cape Cod. Nearly 300 barrier islands rim the Gulf and Atlantic coasts. The islands along the coast of North Carolina are excellent examples. Figure 17.15 Full alternative text description. Most barrier islands are 1 to 5 kilometers wide and 15 to 30 kilometers long. The tallest features are sand dunes, which usually reach heights of 5 to 10 meters. In a few areas, unvegetated dunes are more than 30 meters high. The lagoons separating these narrow islands from the shore represent zones of relatively quiet water that allow small craft traveling between New York and northern Florida to avoid the rough waters of the North Atlantic. Figure 17.15 Barrier Islands. Barrier islands form in several ways. Some originated as spits that were severed from the mainland by wave erosion or by the general rise in sea level after the last episode of glaciation. Others are created when turbulent waters in the line of breakers heap up sand scoured from the ocean floor. Because these sand barriers rise above normal sea level, the sand likely piles up as a result of the work of storm waves at high tide. Finally, some barrier islands may be former sand dune ridges that originated along the shore during the last glacial period, when sea level was lower. When the ice sheets melted, sea level rose and flooded the area behind the beach dune complex. Did you know? Along shorelines composed of unconsolidated material rather than solid rock, the rate of erosion by breaking waves can be extraordinary. In parts of Britain, where waves have the easy task of eroding glacial deposits of sand, gravel, and clay, the coast has been worn back 3 to 5 kilometers since Roman times. Waves have swept away many villages and ancient landmarks. The evolving shore. A shoreline continually undergoes modification, regardless of its initial configuration. Along a coastline that is characterized by varied geology, the pounding surf may at first increase its irregularity because the waves will erode the weaker rocks more easily than the stronger ones. However, if a shoreline remains tectonically stable, marine erosion and deposition will eventually produce a straighter, more regular coast. Figure 17.16 illustrates the evolution of an initially irregular coast. As waves erode the headlands, creating cliffs and a wave-cut platform, sediment is carried along the shore. Some material is deposited in the bays, while other debris is formed into spits and behemoth bars. At the same time, rivers fill the bays with sediment. Ultimately, a generally straight, smooth coast results. These diagrams illustrate changes that can take place through time along an initially irregular coastline that remains relatively stable. The diagrams also illustrate many of the features described in section 17.3. Figure 17.16 The evolving shore. Figure 17.16 Full alternative text description. Concept checks 17.3. 1. How is a marine terrace related to a wave-cut platform? 2. Describe the formation of each labeled feature in figure 17.16. 3. List 3 ways that a barrier island may form. 17.4 Contrasting America's coasts. Distinguish between emergent and submergent coasts. Contrast the erosion problems faced on the Atlantic and Gulf coasts with those along the Pacific coast. The shoreline along the Pacific coast of the United States is strikingly different from that of the Atlantic and Gulf Coast regions. Some of the differences are related to plate tectonics. The West Coast represents the leading edge of the North American plate, and thus, it experiences active uplift and deformation. By contrast, the East Coast is far from any active plate boundary and is relatively quiet tectonically. Because of this basic geologic difference, the types of shoreline erosion problems along America's opposite coasts are different. Coastal classification. The great variety of shorelines demonstrates their complexity. Indeed, to understand any particular coastal area, many factors must be considered, including rock types, size and direction of waves, frequency of storms, tidal range, and offshore topography. In addition, recall from Chapter 15 that practically all coastal areas were affected by the worldwide rise in sea level that accompanied the melting of ice sheets following the last glacial maximum. Finally, tectonic events that elevate or drop the land or change the volume of ocean basins must be taken into account. The numerous factors that influence coastal areas make shoreline classification difficult. Many geologists classify coasts based on the changes that have occurred with respect to sea level. This commonly used classification divides coasts into two general categories, emergent and submergent. Emergent coasts develop because an area experiences either uplift of the land or a drop in sea level. Conversely, submergent coasts are created when sea level rises or the land subsides. Emergent coasts. In some areas, the coast is clearly emergent because rising land or a falling sea level exposes wave-cut cliffs and platforms. Excellent examples include portions of coastal California, where uplift has occurred in the recent geologic past. The marine terrace shown in figure 17.12 illustrates this situation. In the case of the Palos Verdes Hills, south of Los Angeles, 7 different terrace levels exist, indicating 7 episodes of uplift. The ever-persistent sea is now cutting a new platform at the base of the cliff. If uplift follows, it too will become an elevated marine terrace. Other examples of emergent coasts include regions that were once buried beneath great ice sheets. When glaciers were present, their weight depressed the crust, and when the ice melted, the crust began gradually to spring back. Consequently, prehistoric shoreline features may now be found high above sea level. The Hudson Bay region of Canada is such an area. Portions of it are still rising at a rate of more than 1 centimeter per year. Submergent coasts. In contrast to the preceding examples, other coastal areas show definite signs of submergence. Shorelines that have been submerged in the relatively recent past are often highly irregular because the sea typically floods the lower reaches of river valleys flowing into the ocean. The ridges separating the valleys, however, remain above sea level and project into the sea as headlands. These drowned river mouths, which are called estuaries, characterize many coasts today. Along the Atlantic coastline, the Chesapeake and Delaware Bays are examples of large estuaries created by submergence. The picturesque coast of Maine, particularly in the vicinity of Acadia National Park, is another excellent example of an area that was flooded by the post-glacial rise in sea level and transformed into a highly irregular coastline. Smart Figure 17.17 East Coast Estuaries. The lower portions of many river valleys were flooded by the rise in sea level that followed the end of the Quaternary Ice Age, creating large estuaries, such as Chesapeake and Delaware Bays. Keep in mind that most coasts have complicated geologic histories. With respect to sea level, at various times many coasts have emerged and then submerged. Each time, they may retain some of the features created during the previous situation. Watch tutorial, East Coast Estuaries. Atlantic and Gulf Coasts. Much of the coastal development along the Atlantic and Gulf coasts has occurred on barrier islands. Typically, a barrier island, also termed a barrier beach or coastal barrier, consists of a wide beach that is backed by dunes and separated from the mainland by marshy lagoons. The broad expanses of sand and exposure to the ocean have made barrier islands exceedingly attractive sites for development. Unfortunately, development has taken place more rapidly than our understanding of barrier island dynamics has increased. Because barrier islands face the open ocean, they receive the full force of major storms that strike the coast. When a storm occurs, the barriers absorb the energy of the waves primarily through the movement of sand. Figure 17.18, which shows changes at Cape Hatteras National Seashore, reinforces this point. The process and problems that result were recognized years ago and accurately described as follows. Waves may move sand from the beach to offshore areas or, conversely, into the dunes. They may erode the dunes, depositing sand onto the beach or carrying it out to sea, or they may carry sand from the beach and the dunes into the marshes behind the barrier, a process known as overwash. The common factor is movement. Just as a flexible reed may survive a wind that destroys an oak tree, so the barriers survive hurricanes and nor'easters and not through unyielding strength but by giving before the storm. This picture changes when a barrier is developed for homes or as a resort. Storm waves that previously rushed harmlessly through gaps between the dunes now encounter buildings and roadways. Moreover, since the dynamic nature of the barriers is readily perceived only during storms, homeowners tend to attribute damage to a particular storm, rather than to the basic mobility of coastal barriers. With their homes or investments at stake, local residents are more likely to seek to hold the sand in place and the waves at bay than to admit that development was improperly placed to begin with. Frank Lowenstein, Beaches or Bedrooms, The Choice as Sea Level Rises, Oceanus 28, page 22 Woods Hole Oceanographic Institute. After the failure of a number of efforts to protect this 21-story lighthouse, the nation's tallest lighthouse, from being destroyed due to a receding shoreline, the structure finally had to be moved. Figure 17.18 Relocating the Cape Hatteras Lighthouse. Figure 17.18 Full alternative text description. Pacific Coast. In contrast to the broad, gently sloping coastal plains of the Atlantic and Gulf coasts, much of the Pacific coast is characterized by relatively narrow beaches that are backed by steep cliffs and mountain ranges. The chapter opening photo provides a good example. Recall that America's western margin is a more rugged and tectonically active region than the eastern margin. Because uplift continues, a rise in sea level in the west is not so readily apparent. Nevertheless, like the shoreline erosion problems facing the Atlantic coast's barrier islands, West Coast difficulties also stem largely from the human alteration of a natural system. A major problem facing the Pacific shoreline, and especially portions of Southern California, is a significant narrowing of many beaches. The bulk of the sand on many of these beaches is supplied by rivers that transport it from the mountains to the coast. Over the years, this natural flow of material to the coast has been interrupted by dams built for irrigation and flood control. The reservoirs effectively trap the sand that would otherwise nourish the beach environment. When the beaches were wider, they protected the cliffs behind them from the force of storm waves. Now, however, the waves move across the narrowed beaches without losing much energy and cause more rapid erosion of the sea cliffs. Figure 17.1 provides an example. In efforts over the years to halt cliff retreat at Pacifica, California, the city piled rocks along the beach, drilled reinforcement rods into the bluffs, and coated the face of the cliffs with reinforced concrete. Ultimately, the Pacific Ocean won the battle. Figure 17.19 Pacoima Dam and Reservoir. Dams such as this one in the San Gabriel Mountains near Los Angeles trap sediment that otherwise would have nourished beaches along the nearby coast. Shoreline erosion along the Pacific coast varies considerably from year to year, largely because of the sporadic occurrence of storms. As a result, when the infrequent but serious episodes of erosion occur, the damage is often blamed on the unusual storms and not on coastal development or the sediment-trapping dams that may be great distances away. As sea level rises at an increasing rate in the years to come, increased shoreline erosion and sea cliff retreat should be expected along many parts of the Pacific coast. Coastal vulnerability to sea level rise is examined in more detail as part of a discussion of the possible consequences of global warming in Chapter 20. Concept check 17.4. 1. Are estuaries associated with submergent or emergent coasts? Explain. 2. What observable features would lead you to classify a coastal area as emergent? 3. Briefly describe what happens when storm waves strike an undeveloped barrier island. 4. How might building a dam on a river that flows to the sea affect a coastal beach? 17.5 Hurricanes, the ultimate coastal hazard. Describe the basic structure and characteristics of a hurricane and the three broad categories of hurricane destruction. Whirling tropical cyclones, the greatest storms on Earth, occasionally have wind speeds exceeding 300 km per hour. In the United States they are known as hurricanes, in the Western Pacific they are called typhoons, and in the Indian Ocean they are simply called cyclones. No matter which name is used, these storms are among the most destructive of natural disasters. Figure 17.20 Hurricane Patricia. This satellite image from October 23, 2015, shows a hurricane over the eastern Pacific Ocean near the west coast of Mexico. With sustained winds of 352 km per hour, it was the strongest hurricane ever recorded in the Western Hemisphere. Fortunately, the storm quickly weakened after making landfall. The counterclockwise spiral of the clouds indicates that it is a northern hemisphere storm. In the southern hemisphere, the spiral of a cyclone is clockwise. Did you know? Hurricane season is different in different parts of the world. People in the United States are usually most interested in Atlantic storms. The Atlantic hurricane season officially extends from June 1 through November 30. More than 97% of tropical activity in that region occurs during this 6-month span. Statistically, the heart of the season is August through October, and peak activity is in early to mid-September. The vast majority of hurricane-related deaths and damage are caused by relatively infrequent yet powerful storms. Of course, the deadliest and most costly storm in recent memory occurred in August 2005, when Hurricane Katrina devastated the Gulf Coast of Louisiana, Mississippi, and Alabama. Although hundreds of thousands of people fled before the storm made landfall, thousands of others were caught by the storm. In addition to the human suffering and tragic loss of life that were left in the wake of Hurricane Katrina, the financial losses caused by the storm are practically incalculable. Our coasts are vulnerable. People are flocking to live near the ocean. The concentration of large numbers of people near the shoreline means that hurricanes place millions at risk. Moreover, the potential costs of property damage are incredible. As sea level continues to rise in coming decades, low-lying, densely populated coastal areas will become even more vulnerable to the destructive effects of major storms. Profile of a hurricane. A hurricane is a heat engine that is fueled by the energy liberated when huge quantities of water vapor condense. The amount of energy produced by a typical hurricane in just a single day is truly immense. To get the engine started, a large quantity of warm, moist air is required, and a continuous supply is needed to keep it going. Hurricane formation. As the graph in Figure 17.21 illustrates, hurricanes most often form in late summer and early fall. It is during this span that sea surface temperatures reach 27 degrees Celsius or higher and are thus able to provide the necessary heat and moisture to the air. This ocean water temperature requirement explains why hurricane formation over the relatively cool waters of the South Atlantic and eastern South Pacific is extremely rare. For the same reason, few hurricanes form poleward of 20 degrees latitude. Although water temperatures are sufficiently high, hurricanes do not develop within about 5 degrees of the equator because the Coriolis effect is too weak there. Figure 17.23 shows the regions where most hurricanes form. Frequency of tropical storms and hurricanes from May 1 through December 31 in the Atlantic Basin. The graph shows the number of storms to be expected over a span of 100 years. The period from late August through October is clearly the most active. Figure 17.21 When do Atlantic hurricanes occur? Figure 17.21 Full alternative text description. Among the necessary ingredients for a hurricane is warm ocean temperatures above 27 degrees Celsius. This color-coded satellite image from June 1, 2010, shows sea surface temperatures at the beginning of hurricane season. Figure 17.22 Sea surface temperatures. Figure 17.22 Full alternative text description. The map shows the regions where most hurricanes form as well as their principal months of occurrence and the tracks they most commonly follow. Hurricanes do not develop within about 5 degrees of the equator because the Coriolis effect there is too weak. Because warm ocean surface temperatures are necessary for hurricane formation, hurricanes seldom form poleward of 20 degrees latitude or over the cool waters of the South Atlantic and the eastern South Pacific. Smart Figure 17.23 Full alternative text description. Smart Figure 17.23 Hurricane source regions and paths. Watch tutorial, Hurricanes. Pressure gradient. Hurricanes are intense low-pressure centers, which means that as you move toward the center of the storm, air pressure gets lower and lower. Such storms are said to have a very steep pressure gradient. Pressure gradient refers to how rapidly the pressure changes per unit distance and is shown on a map with isobars, lines of equal pressure. Just as the spacing of contour lines on a topographic map indicates how steep or gentle a slope is, the spacing of isobars on a weather chart shows how rapidly air pressure is changing. Closely spaced isobars indicate a steep pressure gradient and stronger winds. A steep pressure gradient generates the rapid, inward spiraling winds of a hurricane. As the air rushes toward the center of the storm, its velocity increases. This is similar to skaters with their arms extended spinning faster as they pull their arms in close to their bodies. Storm structure. As the inward rush of warm, moist surface air approaches the core of a storm, it turns upward and ascends in a ring of cumulonimbus cloud towers. This donut-shaped wall of intense convective activity surrounding the center of the storm is called the eye wall. It is here that the greatest wind speeds and heaviest rainfall occur. Surrounding the eye wall are curved bands of clouds that trail away in a spiral fashion. Near the top of the hurricane, the airflow is outward, carrying the rising air away from the storm center, thereby providing room for more inward flow at the surface. Smart Figure 17.24 Full Alternative Text Description. Smart Figure 17.24 Cross-section of a hurricane. At the very center of the storm is the eye of the hurricane. This well-known feature is a zone about 20 kilometers in diameter where precipitation ceases and winds subside. It offers a brief but deceptive break from the extreme weather and the enormous curving wall clouds that surround it. The air within the eye gradually descends and heats by compression, making it the warmest part of the storm. Although many people believe that the eye is characterized by clear blue skies, this is usually not the case because the subsidence in the eye is seldom strong enough to produce cloudless conditions. Although the sky appears much brighter in this region, scattered clouds at various levels are common. Hurricane destruction. Although hurricanes are tropical or subtropical in origin, their destructive effects can be experienced far from where they originate. For example, in 2012 Hurricane Sandy originated in the Caribbean Sea and affected the entire eastern seaboard from Florida to Maine. Destruction was especially great in New Jersey and New York, even though Sandy was downgraded from hurricane status by that time. Watch video, Cross-section of a hurricane. The amount of damage caused by a hurricane depends on several factors, including the size and population density of the area affected and the shape of the ocean bottom near the shore. The most significant factor, of course, is the strength of the storm itself. By studying past storms, a scale called the Saffir-Simpson Hurricane Scale was established to rank the relative intensities of hurricanes. As Table 17.1 indicates, a Category 5 storm is the worst possible, and a Category 1 hurricane is least severe. Table 17.1 Full Alternative Text Description. Table 17.1 Saffir-Simpson Hurricane Scale. During the hurricane season, it is common to hear scientists and reporters alike use the numbers from the Saffir-Simpson scale. When Hurricane Katrina made landfall, sustained winds were 200 km per hour, making it a strong Category 3 storm. Storms that fall into Category 5 are rare. Hurricane Camille, a 1969 storm that caused catastrophic damage along the coast of Mississippi, is one well-known example. Once a hurricane makes landfall, it loses energy because it is cut off from its energy source, warm ocean water, and is usually downgraded to a lower category. However, these storms are so large and violent that their effects are often felt far inland. Damage caused by hurricanes can be divided into three categories: storm surge, wind damage, and inland flooding. Storm surge. Without question, the most devastating damage in the coastal zone is caused by storm surge. It not only accounts for a large share of coastal property losses but is also responsible for a high percentage of all hurricane-caused deaths. A storm surge is a dome of water 65 to 80 kilometers wide that sweeps across the coast near the point where the eye makes landfall. If all wave activity were smoothed out, the storm surge would be the height of the water above normal tide level. In addition, tremendous wave activity is superimposed on the surge. This surge of water can inflict immense damage on low-lying coastal areas. Figure 17.25 and Figure 17.2 are both good examples. The worst surges occur in places like the Gulf of Mexico, where the continental shelf is very shallow and gently sloping. In addition, local features such as bays and rivers can cause the surge to double in height and increase in speed. This is Crystal Beach, Texas, on September 16, 2008, 3 days after Hurricane Ike came ashore. At landfall, the storm had sustained winds of 165 km per hour. The extraordinary storm surge caused most of the damage shown here. Figure 17.25 Storm surge destruction. As a hurricane advances toward the coast in the northern hemisphere, storm surge is always most intense on the right side of the eye, where winds are blowing toward the shore. On this side of the storm, the forward movement of the hurricane also contributes to the storm surge. In Figure 17, 26. Assume that a hurricane with peak winds of 175 km per hour is moving toward the shore at 50 km per hour. In this case, the net wind speed on the right side of the advancing storm is 225 km per hour. On the left side, the hurricane's winds are blowing opposite the direction of storm movement, so the net winds are away from the coast at 125 km per hour. Along the shore facing the left side of the oncoming hurricane, the water level may actually decrease as the storm makes landfall. Figure 17.26. An approaching hurricane. This hypothetical northern hemisphere hurricane, with peak winds of 175 km per hour, is moving toward the coast at 50 km per hour. On the right side of the advancing storm, the 175 km per hour winds are in the same direction as the movement of the storm. Therefore, the net wind speed on the right side of the storm is 225 km per hour toward the coast. On the left side, the hurricane's winds are blowing opposite the direction of storm movement, so the net winds of 125 km per hour are away from the coast. Storm surge will be greatest along the part of the coast hit by the right side of the advancing hurricane. Figure 17.26. Full alternative text description. Did you know? The difference between a hurricane and a tropical storm is related to intensity. Both are tropical cyclones, circular zones of low pressure with strong, inward spiraling winds. When sustained winds are between 37 and 74 miles per hour, the cyclone is called a tropical storm. It is during this phase that a name is given. When the cyclone's sustained winds exceed 74 miles per hour, it has reached hurricane status. Wind damage. Destruction caused by wind is perhaps the most obvious of the classes of hurricane damage. Debris such as signs, roofing materials, and small items left outside become dangerous flying missiles during hurricanes. For some structures, the force of the wind is sufficient to cause total ruin. Mobile homes are particularly vulnerable. High-rise buildings are also susceptible to hurricane-force winds. Upper floors are most vulnerable because wind speeds usually increase with height. Recent research suggests that people should stay below the 10th floor of a building but remain above any floors at risk for flooding. In regions with good building codes, wind damage is usually not as catastrophic as storm surge damage. However, hurricane-force winds affect a much larger area than storm surge and can cause huge economic losses. For example, in 1992 it was largely the winds associated with Hurricane Andrew that produced more than $25 billion of damage in southern Florida and Louisiana. Hurricanes sometimes produce tornadoes that contribute to the storm's destructive power. Studies have shown that more than half of the hurricanes that make landfall produce at least one tornado. In 2004, the number of tornadoes associated with tropical storms and hurricanes was extraordinary. Tropical Storm Bonnie and 5 landfalling hurricanes, Charlie, Francis, Gaston, Ivan, and Jean, produced nearly 300 tornadoes that affected the southeastern and mid-Atlantic states. Heavy rains and inland flooding. The torrential rains that accompany most hurricanes bring a third significant threat: flooding. Whereas the effects of storm surge and strong winds are concentrated in coastal areas, heavy rains may affect places hundreds of kilometers from the coast for up to several days after the storm has lost its hurricane-force winds. In September 1999, Hurricane Floyd brought flooding rains, high winds, and rough seas to a large portion of the Atlantic seaboard. More than 2.5 million people evacuated their homes from Florida north to the Carolinas and beyond. It was the largest peacetime evacuation in U.S. history up to that time. Torrential rains falling on already saturated ground created devastating inland flooding. Altogether, Floyd dumped more than 48 centimeters of rain on Wilmington, North Carolina, with 33.98 centimeters falling in a single 24-hour span. Another well-known example is Hurricane Camille. Although this storm is best known for its exceptional storm surge and the devastation it brought to coastal areas, the greatest number of deaths associated with this storm occurred in the Blue Ridge Mountains of Virginia 2 days after Camille's landfall. Many places received more than 25 centimeters of rain. Concept check 17.5. 1. What factors influence where and when hurricane formation takes place? 2. Distinguish between the eye and eye wall of a hurricane. 3. What are the three broad categories of hurricane damage? Which one is responsible for the greatest number of hurricane-related deaths? 4. Which side of an advancing hurricane in the northern hemisphere has the strongest winds and highest storm surge, right or left? Explain. 17.6 Stabilizing the shore. Summarize the ways in which people deal with shoreline erosion problems. Compared with natural hazards such as earthquakes, volcanic eruptions, and landslides, shoreline erosion is often perceived to be a more continuous and predictable process that appears to cause relatively modest damage to limited areas. In reality, the shoreline is a dynamic place that can change rapidly in response to natural forces. Exceptional storms are capable of eroding beaches and cliffs at rates that greatly exceed the long-term average. Such bursts of accelerated erosion not only significantly affect the natural evolution of a coast but also can have a profound impact on people who reside in the coastal zone. Erosion along our coasts causes significant property damage. Huge sums are spent annually not only to repair damage but also to prevent or control erosion. Already a problem at many sites, shoreline erosion is certain to become an increasingly serious problem as extensive coastal development continues. During the past 100 years, growing affluence and increasing demands for recreation have brought unprecedented development to many coastal areas. As both the number and the value of buildings have increased, so too have efforts to protect property from storm waves by stabilizing the shore. Also, controlling the natural migration of sand is an ongoing struggle in many coastal areas. Such interference can result in unwanted changes that are difficult and expensive to correct. Hard stabilization. Structures built to protect a coast from erosion or to prevent the movement of sand along a beach are collectively known as hard stabilization. Hard stabilization can take many forms and often results in predictable yet unwanted outcomes. Hard stabilization includes jetties, groins, breakwaters, and seawalls. Jetties. Since relatively early in America's history, a principal goal in coastal areas has been the development and maintenance of harbors. In many cases, this has involved the construction of jetty systems. Jetties are usually built in pairs and extend into the ocean at the entrances to rivers and harbors. With the flow of water confined to a narrow zone, the ebb and flow caused by the rise and fall of the tides keep the sand in motion and prevent deposition in the channel. However, as illustrated in Figure 17.27, a jetty may act as a dam against which the longshore current and beach drift deposit sand. At the same time, wave activity removes sand on the other side. Because the other side is not receiving any new sand, there is soon no beach at all. These structures are built at the entrances to rivers and harbors and are intended to prevent deposition in the navigation channel. The photo is an aerial view at Santa Cruz Harbor, California. Figure 17.27 Jetties. Groins. To maintain or widen beaches that are losing sand, groins are sometimes constructed. A groin is a barrier built at a right angle to the beach to trap sand that is moving parallel to the shore. Groins are usually constructed of large rocks but may also be composed of wood. These structures often do their job so effectively that the longshore current beyond the groin becomes sand-starved. As a result, the current erodes sand from the beach on the downstream side of the groin. To offset this effect, property owners downstream from the structure may erect a groin on their property. In this manner, the number of groins multiplies, resulting in a groin field. The New Jersey shoreline is a good example of groin proliferation, where hundreds of these structures have been built. Because it has been shown that groins often do not provide a satisfactory solution, they are no longer the preferred choice for keeping beach erosion in check. These wall-like structures trap sand that is moving parallel to the shore. This series of groins is along the shoreline near Chichester, Sussex, England. Breakwaters and seawalls. Figure 17.28 Groins. Hard stabilization can be built parallel to the shoreline. One such structure is a breakwater, which protects boats from the force of large breaking waves by creating a quiet water zone near the shoreline. However, when a breakwater is constructed, the reduced wave activity along the shore behind the structure may allow sand to accumulate. If this happens, the marina will eventually fill with sand, while the downstream beach erodes and retreats. At Santa Monica, California, where the building of a breakwater has created such a problem, the city uses a dredge to remove sand from the protected quiet water zone and deposit it downstream, where longshore currents and beach drift continue to move the sand down the coast. Aerial view of a breakwater at Santa Monica, California. The structure appears as a line in the water behind which many boats are anchored. The construction of the breakwater disrupted longshore transport and caused the seaward growth of the beach. Figure 17.29 Breakwater. Figure 17.29 Full alternative text description. Another type of hard stabilization built parallel to the shoreline is a seawall, which is designed to armor the coast and defend property from the force of breaking waves. Waves expend much of their energy as they move across an open beach. Seawalls cut this process short by reflecting the force of unspent waves seaward. As a consequence, the beach to the seaward side of the seawall experiences significant erosion and may in some instances be eliminated entirely. Once the width of the beach is reduced, the seawall is subjected to even greater pounding by the waves. Eventually this battering causes the wall to fail, and a larger, more expensive wall must be built to take its place. Seabright in northern New Jersey once had a broad, sandy beach. A seawall 5 to 6 meters high and 8 kilometers long was built to protect the town and the railroad that brought tourists to the beach. After the wall was built, the beach narrowed dramatically. Figure 17.30 Seawall. The wisdom of building temporary protective structures along shorelines is increasingly questioned. Many coastal scientists and engineers are of the opinion that halting an eroding shoreline with protective structures benefits only a few and seriously degrades or destroys the natural beach and the value it holds for the majority. Protective structures divert the ocean's energy temporarily from private properties but usually refocus that energy on the adjacent beaches. Many structures interrupt the natural sand flow in coastal currents, robbing affected beaches of vital sand replacement. Alternatives to hard stabilization. Armoring the coast with hard stabilization has several potential drawbacks, including the cost of the structure and the loss of sand on the beach. Alternatives to hard stabilization include beach nourishment and relocation. Did you know? Communities along the Atlantic coast of southern Florida have been replenishing their beaches with dredged-up sand for decades. The result is that many areas have exhausted their supply of offshore sand that is environmentally sound and easily accessible. One proposed solution that is under consideration is to grind up recycled glass and transform it into beach sand. Beach nourishment. One approach to stabilizing shoreline sands without hard stabilization is beach nourishment. As the term implies, this practice involves adding large quantities of sand to the beach system. Extending beaches seaward makes buildings along the shoreline less vulnerable to destruction by storm waves and enhances recreational uses. Without sandy beaches, tourism suffers. Figure 17.31 Beach nourishment. If you visit a beach along the Atlantic coast, it is more and more likely that you will walk into the surf zone atop an artificial beach. The process of beach nourishment is straightforward. Sand is pumped by dredges from offshore or trucked from inland locations. The new beach, however, will not be the same as the former beach. Because replenishment sand is from somewhere else, typically not from another beach, it is new to the beach environment. The new sand is often different in size, shape, sorting, and composition. Such differences pose problems in terms of erodibility and the kinds of life the new sand will support. Beach nourishment is not a permanent solution to the problem of shrinking beaches. The same processes that removed the sand in the first place eventually remove the replacement sand as well. Nevertheless, the number of nourishment projects has increased in recent years, and many beaches, especially along the Atlantic coast, have had their sand replenished many times. Virginia Beach, Virginia, has been nourished more than 50 times. Beach nourishment is costly. For example, a modest project might involve 38,000 cubic meters of sand distributed across about 1 kilometer of shoreline. A good-sized dump truck holds about 7.6 cubic meters of sand. So this small project would require about 5,000 dump truck loads. Many projects extend for many miles. Nourishing beaches typically costs millions of dollars per mile. Changing land use. Instead of building structures such as groins and seawalls to hold the beach in place or adding sand to replenish eroding beaches, another option is available. Many coastal scientists and planners are calling for a policy shift from defending and rebuilding beaches and coastal property in high-hazard areas to relocating storm-damaged buildings in those places and letting nature reclaim the beach. This option is similar to an approach the federal government adopted for river floodplains following the devastating 1993 Mississippi River floods, in which vulnerable structures are either abandoned or relocated on higher, safer ground. A recent example of changing land use occurred on New York's Staten Island following Hurricane Sandy in 2012. The state turned some vulnerable shoreline areas of the island into waterfront parks. The parks act as buffers to protect inland homes and businesses from strong storms while providing the community with needed open space and access to recreational opportunities. Land use changes can be controversial. People with significant nearshore investments want to rebuild and defend coastal developments from the erosional wrath of the sea. Others, however, argue that with sea level rising, the impact of coastal storms will get worse in the decades to come, and off-damaged structures should be abandoned or relocated to improve personal safety and reduce costs. Such ideas will no doubt be the focus of much study and debate as states and communities evaluate and revise coastal land use policies. Did you know? Tides can be used to generate electrical power when a dam is constructed across the mouth of a bay or an estuary in a coastal area that has a large tidal range. The narrow opening between the bay and the open ocean magnifies the variations in water level as tides rise and fall, and the strong in and out flow is used to drive turbines. The largest plant yet constructed is along the coast of France. Concept check 17.6. 1. List at least 3 examples of hard stabilization and describe what each is intended to do. How does each affect distribution of sand on a beach? 2. What are 2 alternatives to hard stabilization, and what are the potential problems associated with each? 17.7 Tides. Explain the cause of tides and their monthly cycles. Describe the horizontal flow of water that accompanies the rise and fall of tides. Tides are daily changes in the elevation of the ocean surface caused by gravitational interactions of Earth with the Moon and Sunday. Their rhythmic rise and fall along coastlines have been known since antiquity. Other than waves, they are the easiest ocean movements to observe. High tide and low tide at Hopewell Rocks on the Bay of Fundy. Tidal flats are exposed during low tide. Figure 17.32 Bay of Fundy tides. Although known for centuries, tides were not explained satisfactorily until Sir Isaac Newton applied the law of gravitation to them. Newton showed that there is a mutual attractive force between 2 bodies and that because oceans are free to move, they are deformed by this force. Hence, ocean tides result from the gravitational attraction exerted upon Earth by the Moon and, to a lesser extent, by the Sun. Causes of tides. It is easy to see how the Moon's gravitational force can cause the water to bulge on the side of Earth nearest the Moon. In addition, however, an equally large tidal bulge is produced on the side of Earth directly opposite the Moon. If Earth were covered to a uniform depth with water, there would be two tidal bulges, one on the side of Earth facing the Moon and the other on the opposite side of Earth. Depending on the Moon's position, tidal bulges may be inclined relative to Earth's equator. In this situation, Earth's rotation causes an observer to experience two unequal high tides during a day. Figure 17.33 Full alternative text description. Figure 17.33 Idealized tidal bulges caused by the Moon. Both tidal bulges are caused, as Newton discovered, by the pull of gravity. Gravity is inversely proportional to the square of the distance between two objects, meaning simply that it quickly weakens with distance. In this case, the two objects are the Moon and Earth. Because the force of gravity decreases with distance, the Moon's gravitational pull on Earth is slightly greater on the near side of Earth than on the far side. The result of this differential pulling is to stretch the solid Earth very slightly. In contrast, the world ocean, which is mobile, is deformed quite dramatically by this effect, producing the two opposing tidal bulges. Because the position of the Moon changes only moderately in a single day, the tidal bulges remain in place while Earth rotates through them. For this reason, if you stand on the seashore for 24 hours, Earth will rotate you through alternating areas of deeper and shallower water. As you are carried into each tidal bulge, the tide rises, and as you are carried into the intervening troughs between the tidal bulges, the tide falls. Therefore, most places on Earth experience two high tides and two low tides each day. Further, the tidal bulges migrate as the Moon revolves around Earth about every 29 days. As a result, the tides, like the time of moonrise, shift about 50 minutes later each day. After 29 days the cycle is complete and a new one begins. In many locations, there may be an inequality between the high tides during a given day. Depending on the position of the Moon, the tidal bulges may be inclined to the equator, as in figure 17.33. This figure illustrates that one high tide experienced by an observer in the northern hemisphere is considerably higher than the high tide half a day later. In contrast, a southern hemisphere observer would experience the opposite effect. Monthly tidal cycle. The primary body that influences the tides is the Moon, which makes one complete revolution around Earth every 29.5 days. The Sun, however, also influences the tides. It is far larger than the Moon, but because it is much farther away, its effect is considerably less. In fact, the Sun's tide-generating effect is only about 46% that of the Moon. Near the times of new and full moons, the Sun and Moon are aligned, and their forces on tides are added together. The combined gravity of these two tide-producing bodies causes larger tidal bulges and deeper tidal troughs, producing a large tidal range. These are called the spring tides, which have no connection with the spring season but occur twice a month, during the time when the Earth, Moon, Sun system is aligned. Conversely, at about the time of the first and third quarters of the Moon, the gravitational forces of the Moon and Sun act on Earth at right angles, and each partially offsets the influence of the other. As a result, the daily tidal range is less. These are called neap tides and they also occur twice each month. Each month, then, there are two spring tides and two neap tides, each about 1 week apart. Earth, Moon, Sun positions influence the tides. Smart figure 17.34 Spring and neap tides. Smart figure 17.34 Full alternative text description. Watch animation, tidal cycle. Tidal currents. Tidal current is the term used to describe the horizontal flow of water that accompanies the rise and fall of the tide. These water movements induced by tidal forces can be important in some coastal areas. Tidal currents flow in one direction during a portion of the tidal cycle and reverse their flow during the remainder. Tidal currents that advance into the coastal zone as the tide rises are called flood currents. As the tide falls, seaward moving water generates ebb currents. periods of little or no current, called slack water, separate flood and ebb. The areas covered and uncovered by these alternating tidal currents are tidal flats. Depending on the nature of the coastal zone, tidal flats vary from narrow strips seaward of the beach to zones that may extend for several kilometers. Although tidal currents are generally not important in the open sea, they can be rapid in bays, river estuaries, straits, and other narrow places.